me just share this. You guys might have seen these little devices before. So some of you know what capacitors are. Some of you have seen these before and, never really thought about them, but they're everywhere. They're everywhere, and they're important enough so that there's an entire chapter in our course. Chapter 25 is dedicated to capacitors because they're everywhere and they're very important. They're very important in electronics. And I mean, to be honest, what I think you could argue that they're actually more important in the area of physiology and cellular biology or cell biology. Specifically, here, check this out. Just before we dive into the deep end, capacitance arises from the fact that the lipid bilayer is so thin that an accumulation of charged particles, yada, yada. Anyway, what you're looking at here is you're looking at the cell membrane, the cell plasma membrane layer. Ever ask yourself, what is it? What is it that separates inside a human cell from outside a human cell? And the answer is a wall, a cellular wall. It's like every cell comes encapsulated in its own sort of envelope, and the envelope is made of a lipid protein, yada, yada, yada. But now here's the cool thing. The cell lets some stuff in and lets some stuff out. So it's very precise. It's very preordained as to which materials can go inside a human cell. I'm saying human cell, but this applies to any animal cell and maybe plant cell. I don't know about plant cells, but stuff is allowed into the cell in the right amounts at the right times. Stuff has to get kicked out of this cell in the right amounts at the right times. And believe it or not, a lot of that control or that control happens via capacitance, where you actually have separated charges down here. If you're seeing my cursor, the charge in this layer, the charge of this sort of inside wall is different compared to the charge of this outside wall. And you're looking at like a hyper magnified cross section or zoom of the human cell. And then in between the wall, in between these layers, you have like this stuff inside. It's like an Oreo cookie. Here's the chocolatey lower wafer and the chocolatey crunchy upper wafer. And in between, you have the white, the white frosting. And in this case, the frosting actually is called a dielectric. And anyway, there's lots of electrical engineering. There's lots of electronics in biology. So anyway, just wanted to go down that rat hole for a minute. Let's go to chapter 20, the quiz, chapter 25, quiz 1. And let me know if you don't see it, because I'm thinking you're seeing it, and I'm thinking it should look like this. Capacitors. All right, this should be chapter 25, quiz 1, and I'm still getting my signals crossed sometimes because of various learning curves. I'm still going up with this new Wiley Plus, but this is this problem, the first of, and there's not many homework problems for this chapter. And there's a few basic categories in capacitors. So this is the theme of this problem is talking about capacitors in, so caps for short. Caps is short for capacitors. Caps in series and parallel. That's the main takeaway from this problem. Capacitors in series and in parallel, and blending them together. So let's solve this problem. But before we do, just another little sidebar, just because if we just start solving this problem now, although you watch the YouTube lecture video. So let me just give you the 25-cent tour of capacitors. The $100 tour is what you get when you watch the YouTube green sheet lecture. But just to a brief recap, this is why we love capacitors. We love capacitors because of what's going to happen right now. I'm going to turn on this battery, and you see when I turn on that battery, when I turn on a power source, you have all of this charge accumulation on these capacitors. This is a parallel plate capacitor. You actually covered this in chapter 22, and then again in chapter 23, and then again in chapter 25. So you're you're hitting these parallel plate capacitors 3 times. So again, underscoring that they are pretty important. We like capacitors because they do this. They allow charges to accumulate on their top and bottom plates. So that's pretty good. But now watch what happens when I disconnect this capacitor from the circuit. This is why we really like capacitors right now, what you're looking at, because now I have this capacitor that's disconnected from an energy source, and yet it's still energized. So this is why capacitors are kind of like batteries. They store energy. They don't make their own energy. Batteries make their own energy via electrochemical processes, and they are sources of energy, whereas a capacitor is an energy repository. This is why if you ever drive around and you see these giant wind farms, for example, here's a gigantic wind farm right here. This actually looks familiar. So, I mean, the great thing about wind is that it's clean energy in many ways, although it's not. There's actually growing debate about, are we doing wind energy the right way? Because there's pros and cons. I think the pros are profound, but there are cons to wind energy. One of the cons, I don't think this is the biggest con, but one of the cons is how do you store this energy? What do you do if it's not a windy day? If it's a windy day, great, you can run your electronic devices. If it's not a windy day, you're out of luck and you have to have other sources. But one of the, and you know what, that comment there is the same as you would say for a solar collector firm. Solar energy is really up and coming. It's becoming very mainstream. And here's a picture of a solar farm. One of these is in Ann Arbor, not too far from here, across from the School of Music, where I used to go twice a week for years and years. But here, let me just, there is a giant solar farm. And sort of it's the same story here. There's the commonality between solar and wind is it's great if the sun's out or if the wind's blowing, but what happens, if the sun's not out and the wind's not blowing? The goal is to figure out ways to store this energy. I mean, these devices are pretty good at generating electricity, but there's a lot of new age, new school research, cutting edge research going into something known as supercapacitors. Supercapacitors, basically making capacitors, making energy storage devices that are truly large scale enough and resilient enough to store these huge amounts of electricity that are generated by wind and solar. And these really aren't the pictures. It's still very, well, this is kind of it. It's very, lots of physics in supercapacitors. What is a supercapacitor and how does it work? Well, the pictures aren't coming up. But anyway, I'll just go back to this picture or this visual right here. Back to the 25-cent tour. It was right here. Here. There. This is why we like capacitors, because they do that. Now, here's a little more in-depth reason. Here's sort of a second reason why we like capacitors. I think this is a very primary reason. Look at that. You get all that energy storage. And then if you want to tap into it, you just reconnect it to a circuit. Here's the other reason we like capacitors. This is a circuit, and you'll be doing stuff. You'll be using this simulation. These are great simulations. So I basically made a little circuit, and you see this little parallel plate capacitor. Watch what happens when I switch from this view to that view. So this is called the schematic diagram. And you see these little symbols. It's like hieroglyphics. You see these symbols. This is a battery. This is a switch. That's a capacitor. That's a resistor. So watch what happens if I just toggle. This is sort of like a real view or like an easy. So there's a battery. There's a parallel plate capacitor. There's a resistor. Here's a switch. Oh, there's a fire. Things are on fire. Everyone leave the room. But anyway, and then schematic and real physical. Watch what happens though. I'm going to hook up a voltmeter. Open this switch. 3, 2. Watch this graph. 3, 2, 1. Close this switch. Notice how my voltage. So once again, the capacitor charge is accumulating on the capacitor, and it's not happening instantaneously. And that's actually a profound property of capacitors. They don't happen in the blink of an eye. Let me discharge it. So again, right, technically speaking, this capacitor is completely disconnected from any energy source, and there it is, still energized. So now I'm going to throw this switch. Watch what happens on this voltage versus time curve. 3, 2, 1, close the switch. There. You see how the voltage or the charges basically dissipate, but they don't do so instantaneously. When I charge the capacitor, I get logarithmic growth. So very profoundly mathematical. That is a logarithmic growth curve. And then when I discharge this capacitor, I get exponential decay. And the fact that it behaves this way makes them very useful in a number of different applications. The fact that they have this mathematical predictability means you can use them in intelligent ways. So back to that's again, the 25-cent tour. That hopefully, what's your appetite for the $100 tour coming your way via the YouTube lecture videos? We can go back to chapter 25, quiz 1, and we just have a whole bunch of capacitors in series and in parallel. And here's the task at hand. We actually have to figure out the capacitance on capacitor 1 and capacitor 2. Let me make this a little bit bigger. All right. I am going to index some things here. There's capacitor 1, capacitor 2. Here's capacitor 3, 4, 5. All right, so I'm going to call this 1, 2, 3, 4, 5. So here I have a bunch of capacitors, sort of all connected in certain ways. And we love capacitors because they store energy and they have this mathematical behavior. And the question is, what is the charge on capacitor 1, which is right here? And what's the charge on capacitor 2, which is right here? Let us begin. I'm gonna go after the easy one first. So here's step number 1. Well, I'll apply par V for capacitor 1. Capacitor number 1, which I'll just write as C1. Par V talked about ad nauseum via the lecture videos. I'll just give you again, everything is going to just be highly compressed in terms of my background stories now. But I'll just say this, par V. It's a mnemonic. Par V means elements in parallel, elements arranged in a parallel configuration share the same voltage. So instead of saying elements arranged in a parallel configuration share the same voltage, I'll just say par V. And whenever you hear or you say par V, that's what it means. Elements in parallel share the same voltage. And it turns out C1, which is right here, and this voltage supply are in parallel. So this voltage, just think of this as like a battery. So this little schematic here is a battery. So when you see a long line and a short line, when you see this symbol, this is a battery. By convention, this is always the positive terminal of the battery, and this is always the negative terminal of a battery. And just in case you're wondering, what's a terminal of a battery? Battery terminal. Let's just get a quick view of that. Battery positive terminal of a 1.5 volt battery. Okay, here, this is pretty good. All right. This is a good picture, I think.
You're not sharing your screen.
I know, give me 1 second. I don't quite have it yet. Open in new tab. Okay. Not the image I'm looking for, but here. All right. You guys have seen these batteries. You guys, these batteries are everywhere. And you can see that little positive mark on this battery. Positive stands for the positive terminal of the battery. And sort of the other side of the battery is negative. Even though it's not marked negative, we know it's negative because we know what the positive is. So battery 0.5 volt. 1 second, one more time. And all right. Well, okay. Here. Maybe this is better. Not really. I'm just looking for a bigger picture. But anyway, that is what's meant by the positive terminal of a battery and the negative terminal of a battery. All right. So this battery, V for voltage, where does the voltage come from in a battery? It comes from an electrochemical process. If you've ever cut apart a battery, if you've ever like stripped a battery into like its stuff, there's like a zinc, it's like a can, it's a can made out of zinc and like this black powder, compressed powder inside. It's pretty interesting, really. But very electrochemical. C1, I'll say this before we return to the problem. In this configuration, C1 and the voltage are in parallel. They are in parallel. So par V applies. So I'm just thinking they're in parallel. Think par V, they share the same voltage. And how do I know they're in parallel? And I'll say this probably a whole bunch of times, but notice how they come together at this junction and how they come together at this junction. To be in parallel, parallel means the following. Parallel means two devices are in parallel, and you can sort of see it looks like parallel if they share the same node, if they share a common node on both sides with no devices, no intermediate devices. So there's the formal, I guess, definition or formal description of what it means to be in parallel. Parallel means two devices are in parallel if they share a common, paste a proofread, if they share a common node, on both sides with no intermediate devices. All right, so I'm going to read that one more time. Parallel means two devices are in parallel if they share a common node on both sides with no intermediate devices. So the third proofreading round is a charm. And we have that here. This is a node. This is a node. So check out C1, capacitor 1, and my battery. They share a common node right here. They share that they're both connected to that node. And on the other side, they're both connected to this node, and there's nothing in between them. I don't have like another resistor or another capacitor in between. So that is an explanation as to why C1, the capacitor 1, and the battery are in parallel, which means they share the same voltage. My battery has a voltage of 10 volts. So this is 10 volts, 10 volt battery, which means the capacitor also has a voltage of 10 volts. So that's par V. Par V is saying 10 volt battery, that's in parallel, means 10 volts across my capacitor. So I know two things about this capacitor. I know the voltage. I'm just going to call it my voltage drop. That's how you refer to it. The voltage across, or the voltage of my capacitor C1, which is typically you refer to it as voltage across or voltage drop, is 10 volts. And I know the value, the capacitance of C1 itself is 14 microfarads. So that's two key pieces of information. I know the voltage drop and I know the capacitance value. So, use the Q equals CV equation. So this is, I think, well, this is, there are two very fundamental, there's two ultra fundamental stakes in the ground in terms of chapter 25. There's capacitance. Capacitance equals kappa epsilon naught A over D. And then there's also Q equals CV. So these are really the big two. There's other important equations, and we're going to get to those in short order. But these are again the ultra fundamental. I refer to this as the Q equals CV equation, and this is basically the capacitance equation. So Q equals CV. This is the story Q equals CV is telling. It's saying, hey, if you have a capacitor like C1, in fact, maybe I'll subscript this. Maybe I'll say I'll personalize it. The charge on capacitor 1 is equal to the capacitance of capacitor 1 times the voltage. Maybe I'll just use ones. All right. So there's my personalized Q equals CV equation. And let me just, again, do the read through. It's saying the charge that accumulates across capacitor C1 is equal to the product of its capacitance and its voltage. And again, this is why we like capacitors, because of Q1. We like capacitors because they're energy storage devices. You could argue, I guess, depending on the day of the week or the mood you're in, you could argue, well, no, Chris, really what I like capacitors because they're voltage sources. They're like batteries. Instead of using a battery, you could use a capacitor, and there are profound advantages to capacitors. There's disadvantages too, so you have to just be aware of the application. But anyway, this is the Q equals CV equation that relates charge, capacitance, and voltage. Ultra fundamental. So step number 3 says, all right, so the charge across capacitor 1 is equal to the capacitance of capacitor 1, which is 14 microfarads times the voltage drop across capacitor 1, which is 10 volts. And why is it 10 volts? Par V. So you know what I'm going to get here? I'm going to get 14 times 10 to the minus 6 farads times 10 volts equals 140 E minus 6 farad volts. And if I do the dimensional analysis on a farad volt, I can do it right here using the Q equals CV equation. Question: what are the units for charge? Answer is coulombs. What's the units for capacitance? Farads. I don't know if I've said that yet. Farads is the units of capacitance, and voltage right here. So just by keying on the Q equals CV equation, you can see that capacitance equals farads times voltage. So in this case, that's my answer. I know that a farad times a volt is a coulomb, and I don't even need a calculator. It just equals 140 microcoulombs, because I still have that 10 to the negative 6. So this is going to equal 140 times 10 to the minus 6, or microcoulomb. And again, dimensional analysis says that a farad times a volt is indeed equal to a coulomb. So we're done with part A. Loving the capacitors because they store energy, force, and they behave in a mathematically predictable way, which makes them useful in intelligent applications and in the human cell. But that's it for part A. I'm actually going to wipe the slate clean here. So with all of this good stuff, which is being recorded for your future reference, I'm going to wipe the slate clean and move on to part B. But I just want to hype this just briefly. Part V is really important. Understanding what it means to be in parallel is important. This ultra fundamental equation Q equals CV is very important. So those are the three big takeaways right now for part A. I'm going to wipe the slate clean and do part B, which is going to be a little more involved. All right, so now we have to figure out what is the charge on Q2. I'm going to go back to my numbering, my indexing Q1 or C1, C2, C3, C4, C5. All right. All right, so I'm done with C1. I'm looking at part B. I'll start right here. Number one, I need to collapse. I need to play the collapsing capacitor game. This term, collapsing capacitor game, is literally something I thought of right now, just to give it a label. We're going to play the collapsing capacitor game. So I'm going to go in steps. Here's my battery. This is my battery. There's my positive terminal. There's my negative terminal. There's this wire going up, and then there's that wire going down, and then here's this wire going up. Now here's my first move. I'm going to take these two capacitors right here, C2 and C3, and I'm going to collapse them into an equivalent capacitance. Ready? Here goes. It's going to look like this. I'm going to give it the poetic name of C23. So C23 is what I'm referring to as the equivalent capacitance. C23. All right, so C23, instead of drawing C2 and C3 separately, I'm blending them together. I'm going to leave everything else the same because I'm going to go in baby steps. So then C4, nothing's different about C4. That hasn't got blended yet. And just keep and recreate your circuit. Here's C5, the same as it ever was. C5. And then here's so what I'm drawing here, this is exactly the same circuit, except I've blended C2 and C3 into an equivalent capacitance. And then now we have to look at C2 and C3. So the first question you ask yourself, is this series or parallel? And you can sort of tell just by looking at them. They're in series. Look at how like they're just stacked together. C2 and then C3 is just right next to it, right in line with it. It's like trains of a long, it's like cars of a long locomotive. They're just connected one in front of the other. And they're not in parallel. The definition of parallel that I wrote down doesn't apply here. Here's series. Series means this. Two devices are in series if they're on the same wire, same path, and the current flowing through, or I have to say onto, and the current flowing through or onto C2 is same as current flowing through parentheses onto C3. Let me do a proofread. So you know you're in series. C2 and C3 are in series if they are on the same wire. Okay, that's good. They are on the same wire. C2 and C3 are on the same wire, meaning they're both just sitting on the same path. And the current flowing through C2 is the same as the current flowing through C3, except again, I wrote down in parentheses, current doesn't flow through a capacitor. If charges actually flowed through a capacitor, that is a broken capacitor. You basically have a destroyed capacitor. So that's what I'm saying onto. If the current flowing onto C2 is the same as the current flowing onto C3, and if they're on the same path, they're in series. And plus, visually look at it. I mean, that looks like a series connection versus the parallel connection that we dealt with when we were talking about C1 and V. All right, so that is a lot of conversation, hopefully making it very clear that C2 and C3 are in parallel. So I'm sorry, C2 and C3 are in series. For series capacitors, this is how we find out the equivalent capacitance. For series capacitors, this is what we do. The equivalent capacitance, which I guess I'm calling the equivalent capacitance, I'm saying is C23. C2 and C3 equals 1 over C2 plus 1 over C3. This is the expression you use for two or more capacitors in series. If I had other capacitors in series, I would just say, well, plus C X plus 1 over CY plus 1 over CZ and on and on. But I don't. I only have these two capacitors, C2 and C3. They are for sure in series because I thought hard about it. And this is how you combine them. This expression right here was derived in your green sheets. And I'm just going to make my customary request like, hey, if you guys are going to end up, if you stay on a path towards engineering or science or technology, you have to be the type of person who understands the derivations. It's a separator. All right, so let's get a number on this. This equivalent capacitance, C23, is going to be 1 over C2. They all have capacitance of 14 microfarads plus 1 over C3, 1 over 14 microfarads. And so what is the equivalent capacitance? And here's what you don't really need to do. You don't really need to convert. You don't really have to write this as 14E minus 6 farads at this point. I mean, here's what I'm going to do. I'm just going to leave it as micro. I'm going to leave microfarads sort of intact. So I don't have to say, well, that's E to the minus 6. That's E to the minus 6. Just leave it as microfarads. And when I do this, so now get out your calculator and you can say, what is 1 divided by 14 plus 1 divided by 14? Reciprocal that, 7. So C23 has an equivalent capacitance of 7 microfarads. And this can be tricky, so just make sure you're good on the calculator part. I mean, this will become very easy after a short while, but it's weird at first. 1 divided by 14 plus 1 divided by 14, reciprocal, all of that. 7, that's it. So let's continue the game because we're still playing the collapsing capacitor game. Okay, so I guess you know what I'm looking at. Here's my next move. 1, 2, 3, 4. I'm eyeballing C23 and C4. So this catches my eye. C23 and C4. Those are in parallel. Let's do the litmus test. Are they connected to a common node? Yeah. What I'm drawing here in purple, that's called a node or a junction. So they're connected to the same node on one side. What about the other side? Yeah, they're connected to this node down here. So they share a common node on both sides. Is there any stuff between them No, it's not. It's just them. It's just C23 and C4. Is this a series connection? No, it's not. You know why? Because watch what could happen. Charge could flow into this node, and then some of it could go over here. Some of it could go here. So right there, right what I just, it's definitely not series. This is not a series connection, because remember, a series connection to C23 and C4 are in series if they're on the same wire, meaning the same path, and the current flowing onto C23 is the same as the current flowing onto C4. It doesn't satisfy that criteria. So these are in parallel. So here's let's combine them in parallel. Here's my next drawing. So I just think of this as like cartoon strips. Here's my battery. Here's what I'm going to poetically name C234. C234 is the collapsing or the combination of capacitor C23 and C4. Remember, C23 itself is the combination of C2 and C3 and then C5. Okay. So this is my next move. So here, number 5. C23 and C4 are in parallel. So this is a job. I'll write it down. C23 and C4 are parallel. So let's introduce the equivalent capacitance for two capacitors in parallel. Ready? C234 equals C23 plus C4. It's that easy. So here I had like this reciprocal. This looks pretty complicated. I have this expression to deal with capacitors in series. I have this expression for capacitors in parallel. And again, the full scale conversation about where those equations come from and how they're derived is in the lecture notes. But the equivalent capacitance C234 is C23, which is 7 microfarads, plus C4, which is 14 microfarads, or just 21 microfarads. So progress is being made. Let's continue this game a few more steps. And I'm going, admittedly, I'm going in super small baby steps. When you get enough practice, you're going to be able to do what I do 10 times faster and more efficiently. I don't want to start off at that, at that level. It'd be too much. This is my voltage. My next step, here's my same battery. And then I'm going to do one more collapse. I'm going to call this C2, 3, 4, 5. So it doesn't get any more basic than this. I started with this relatively complicated looking circuit. Looks pretty kind of messy. And then I ended up with something that looks very basic. Can't get any more basic than that. So here we go again. This is still the battery. It's not a capacitor. That's the long. This is my long positive terminal. This is my short negative terminal. Number 8, C2345 question. Here's C234. Here's C5. Are they in parallel or are they in series? They are in series, which I think is obvious. And if it's not obvious, it soon will be. C234 and C5 are in series. So let's treat them like series capacitors. And here's C2, 3, 4, 5 equals 1 over C234 plus 1 over C5. Okay, this is how you deal with two capacitors in series. So with numbers, I have 1 over C234 which is 21 microfarads, plus 1 over C5, which is 14 microfarads. And that is 1 divided by 21 plus 1 divided by 14, reciprocal, 8.4. This is, for me, my numbers, 8.4 microfarads. That is the equivalent capacitance. So that's actually half the task. We basically figured out, we played the collapsing game. I can't collapse this anymore. So now we're going to go in reverse. We're basically we're going to just flip the direction arrow and go backwards. But before we do that, let's do a few other things that we're going to have to figure out. Number 8, 9, 10, 11. 11 says this. What is Q? What is the charge across C2, 3, 4, 5? What is the charge? I need to find out what is the total charge sitting here stored in this capacitor. And you could say, well, Chris, what you really mean is C2, 3, 4. You're basically asking the following. What is the total charge stored in here? What is this total charge stored in C2 plus the total charge stored in C3 plus the total charge in C4 and C5? And that's what I am doing that. I'm saying I need to find out the total amount of charge sitting there, and then start to work backwards. All right, so let's do that. Well, Q equals CV to the rescue. So Q equals CV. This is the Q equals CV equation. As mentioned a while ago, this is one of the two ultra fundamental expressions for chapter 25 for capacitance. So let's just apply this. I'm going to say that the charge across C2, 3, 4, 5 is equal to the capacitance across C2, 3, 4, 5, which is 8.4 microfarads times the voltage drop, which for me is 10 volts. There it is. I have this much. I have 84 microcoulombs. That's a big deal. It's not the answer, but I have 84 microcoulombs sitting in this capacitance right here. 8.4. Let's just double check that. Is everything good to go? 8.4. This is Q equals CV. See, this is 8.4. That looks good. And this is 10 volts. And where did that 10 volts come from? Because par V. So it's going to sound like a lot of stuff is getting thrown at you, but it's to be honest, it's a very limited number of fundamentals. Par V is a fundamental. The Q equals CV is a fundamental. There's like probably literally only 5 or 6 fundamentals that you have to get your arms around and then just get good at applying them. I guess this is good. All right. So now let's do this. Let's work backwards. I'm going to record everything here. I know this is equal to 8.4 microfarads. C234 equals 8.4 microfarads. And then maybe a different color for charge. My total charge is 84 microcoulombs. Okay. Now let's go backwards. So now we go in the opposite direction. I'm going to go from this collapsed to this less collapsed. And I'm going to write down the following. This is 84 microcoulombs stored in C5. This is also 84 microcoulombs stored in C234, which brings us to the other. One more fundamental. There really aren't that many. So don't let your head start spinning. I know mine could start spinning, but Seri Q. Seri Q is the next mnemonic. Seri Q. So there's two mnemonics. There's par V, stuff in parallel has the same voltage, and then there's Seri Q. Seri Q says stuff in series carries the same charge. So I'll write that down. Seri Q means two, or I'll just say capacitors. Capacitors in series contain the same charge. So that's the second of the two big mnemonics. Par V, Seri Q. Again, here's the 25-cent version of Par V and Seri Q. Let me just go into this fantastic FET simulation here. Capacitor lab. FET. FET capacitors. All right. Waiting. Initializing. Okay. So, in a nutshell, here's Seri Q, 3 in series, charging different capacitances. All right, there is a just a at a glance explanation of what Seri Q means. Seri Q, watch what happens when I adjust my battery. So no matter what's going on, because these capacitors, because C1, C2, and C3 are all in series, they carry the same charge. So you're looking at a great visual of that right now. I'm just going to bring this in to the notebook for a minute. And this is exactly how I remember Seri Q. Right here. All right, so Seri Q means, and you can actually see a visual of it, whatever the charge is here, the charge C1, whatever this charge here, charge on capacitor 2, and the charge on capacitor 3, it's all the same. It's all, and here, if we wanted to count it, you could count these little charge symbols. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So here's how it goes. Just for the sake of this conversation, there's 12 positive charges here. There's 12 negative charges here. You know what that means? These 12 negative charges will attract 12 positive charges. These 12 positive charges will attract 12 negative charges. So look how it cascades. These negative 12 charges will attract those 12 charges. And similarly, these 12 positive charges attract these 12 negative charges. So again, just look how it flows. I have positive 12, negative 12, positive 12, negative 12, positive 12, negative 12, even though the capacitances are much different. Look, this has a capacitance of 3, 2.4, 1.9. This is Seri Q. Capacitors in series have the same charge. So there, that is the 25-cent recap. Except I don't, yeah, that's good. All right, so now that we know that, Seri Q, this is why I'm saying I have 84 microcoulombs stored in capacitor C5, and I have 84 microcoulombs stored in capacitor C234. While I'm here, while I'm doodling on capacitor C234, I'll just do this. Seri Q means the charge on C234 equals 84 microcoulombs. Okay, let's find the voltage. So in red, I need to find the voltage across that capacitor. And this is a job for Q equals CV. So to be honest, I don't know if there's anything new that's going to happen. Well, there's a couple. So there's a few new introductions, but I think most of the formal introductions have been made. Actually, they have been made. So that's good. All right. So what is the voltage? What's the voltage drop across capacitor C234? Well, I'm going to start with the Q equals CV equation. If Q equals CV, then V equals Q over C. So personalized for this situation, I have the voltage across C234 is going to equal the charge across C234, which is 84 microcoulombs. That's my numerator, divided by the capacitance of C234. The capacitance of C234 is 21 microfarads. 21 microfarads. And treat this mu, this micro, as just something that you can cancel if it's possible. This micro cancels with that micro. So what is 84 divided by 21? The answer is 4. So this is 4 volts equals 4 volts, because apparently dimensional analysis, Q equals CV means I have coulombs equals farads times volts, which means a coulomb over farad does equal volts. So dimensional analysis looks good. 4 volts. So I'm going to write that down in its own special color. This is 4 volts. Okay. So this is what's happening with this capacitor right here. It has a voltage of 4 volts. The voltage drop across it is 4 volts. So just let's give acknowledgement. Acknowledge 4 volts is the voltage drop across C234. C234 has a charge of, it's storing 84 microcoulombs, and its value is 21 microfarads. Now let's work backwards. I think one more time. So backwards. All right. So you know what I can say here? Now that I'm back to, I'm almost back to square one. C234. Well, if there's 4 volts, if there is 4 volts across this entire, I'm sorry, if there are 4 volts across C234, par V says, well, this is 4 volts, and then this is 4 volts. And again, thanks to par V, let me keep going with that. Number 15. Number 15. Par V means stuff that's in parallel has the same voltage. So par V is saying the voltage across C23 is the same as the voltage across C4 because they are in parallel. I mean, look at it. I think it's pretty obvious. C23 and C4 are in parallel. Whatever the voltage is, it's 4. And I know macroscopically, if this is 4 here, macroscopically, it's only because it's 4 across C23 and 4 across C4. So before we work backwards one more time, what is the charge? It's getting kind of denser. I'm going to go 16. What is the charge stored in C23? What is the charge stored across capacitor 23? Number 17. This is a job for Q equals CV. So Q across C23 equals C23 times V, the voltage across C23. Just doing a lot of subscripting here. All right. So what is the charge across that? Well, what is the capacitance of C23? It's 7 microfarads. What is the voltage across C23? It's 4 volts. 4 volts. So this is, again, the charge stored in C23, Q equals CV, and I'm just double checking. C23 had a value of 7 microfarads. That's the capacitance. The voltage drop across C23, because it's in parallel with C4, and collectively they have to have the same voltage. That's why I'm saying 4 volts. So here's the answer. That charge across the charge stored in capacitors 2 and 3 is 28 microcoulombs. And again, here's how you don't have to convert. I'm just going to keep micro as its own term. And then I know, well, a farad times a volt is a coulomb. Okay. 28 microcoulombs. So now the last step is series Q. Let me get rid of this and then we're done. So I know I'm spending a huge amount of time on this, but really this covers a lot of the basics. There's very little new stuff that's going to happen in this homework set once we're done with this. So that's why the heavy lifting now. Number 20, I'm going to work backwards one more time from here to here, back to here. So C23, those are in series. Clearly, those are in series. It satisfies the criteria. They are on the same path. Whatever the charge is flowing onto C2 is the same as the charge flowing onto C3. So this is a job for series Q. Series Q says the charge on capacitor 2 is the same as the charge on capacitor 3. And I just got that answer. It's the same as the charge on them collectively. C23. And before we close the door on this, I just want to very quickly just make sure that that's clear. Because actually, let me go back. Here, it is saying whatever the charge is on this assembly, collectively speaking, right here. So I am saying, I'll use my example of 12. What is the total charge stored in all 3 of these capacitors? Equals 12, because I have plus 12 here and I have minus 12 here, and then everything else cancels out. Basically, I have, this charge right here. These 12 cancels with these 12. Positive 12 here cancels with negative 12 here. So in aggregate, I have a charge separation of 12 charges. That's what I'm saying. For this entire capacitor, the charge is 12. You don't say, well, I have 12 here and 12 here, so that's 24. And you don't say, well, I have positive 12 here and negative 12 here, so it's 0. No, and this is really a common tripping point. You're looking at 3 capacitors that amongst all 3 of them store a charge of 12, which is why I'm doing that same approach, using that same approach here. I just got done saying C23 is 28 microcoulombs. And for the exact same reason, the exact same visual, this charge here is the same as this charge here, is the same as this charge here, because look, they're all, the C2 and C3 are in series, which is why that's the answer to B. So that is literally 1 hour spent on one problem, but it's going to go a lot faster going forward. And that is 1 hour. Let's see what quiz 2 is looking like. This will go a lot faster, much faster. So let me get quiz 2 ready, and then we'll take a break. there's only one more introduction I need to make, and then that's it for chapter 25. And then there's, of course, the lots of practice. And rewatching the lecture video and rewatching this Zoom recording. Oh, also, you should have your link to the exam 3. The exam 3 traffic light report, which is worth an astounding 2 points of extra credit. Always do 10 p.m. the night before the exam. And you don't have to print anything out. I basically just turn off. I take a snapshot of your spreadsheet. So whatever your spreadsheet looked like at 10 p.m. on Wednesday, that's what you get. And the same will be true for the traffic light report for exam 3 and exam 4. So keep that in mind. Oh, wrong. Chapter 25.
Professor Wood, the exam 3 traffic light report is for view only. Like, we can't edit it.
Is that true for everyone?
I can edit mine.
All right, Mo, I'll take a look at yours specifically and fix it.
Okay, thank you.
And then if I'll do that during a break. If someone else has, definitely let me know, because I'm a true, but you were talking to a true believer. Those exam traffic light reports are just so helpful. Again, I'm thinking my glorious life as a engineering consultant, I had to live on those things. All right, so here's quiz 2. We are going to start chapter 25, quiz 2, which will go much faster. Nice visual situation here. I have 4 capacitors. I have 4 air-filled capacitors, and we're going to get to a point where they're not filled with air. It's going to be like that cell plasma membrane. It's going to have, or the Oreo cookie, and you're going to have the wafers basically encasing something instead of just air. But right now, this is capacitor 1, capacitor 2, capacitor 3, capacitor 4. So I have 4 capacitors air-filled, and here's what they look like if they're not air-filled. There's going to be something, some kind of creamy white filling that is encased in those plates. But right now, these are just air-filled, connected to a larger circuit. So we have a graph. This is voltage versus a position, I guess. Voltage versus position. Okay. Similarly, the graph above. So we have this is the schematic diagram. Yeah. Okay. So what I'm circling here, this is the schematic diagram. Schematic. I'm only showing the schematic symbols for a capacitor. So this is a capacitor only circuit. 1, 2, 3, 4. Okay. And this graph is telling me a lot. Capacitor 3, what are the capacitance of 1 and 2? So before we get into the nitty-gritty, I'm saying according to this graph, it's making life pretty easy. The voltage drop across capacitor 1 is equal to V 12 volts, all right, is going to be equal to 2 volts. 2 volts here. It's saying the voltage difference. And remember, voltage difference is basically like a pressure difference. If you turn on your kitchen faucet and the water comes trickling out very sort of anemically, that's because you have low pressure. If you turn on another faucet and the water comes rushing out at a very high rate, that's because you have high pressure. So again, voltage is analogous to water pressure, using the plumbing analogy, which means basically here in this situation, whatever the voltage here is on this plate compared to the voltage on this plate, this change, whatever that difference is, delta V equals 2 volts. So I have a pressure difference. If there's a pressure difference, which really means charge separation, if I can figure out how to separate charges, which is the whole purpose of a capacitor, those separated charges create a voltage difference, creates a like a water pressure. All right, so what's my voltage drop across V2? The voltage drop across V2 is 5 volts. The voltage drop across V3 is equal to, well, I'm going from 12 to 5. That leaves 5 volts. 12, yeah, 5 volts. Even though it doesn't say 5 volts. How do let me be sure on that. 5 volts. Because this bottom graph is saying 12 volts is sitting here across V4. This bottom graph is referring to the voltage situation with this bottom capacitor number 4. Okay, so this graph is saying my voltage across capacitor 4 is 12 volts. Capacitor 4 is in parallel with C1, 2, and 3. This capacitor number 4 right here, which I'm circling, is in parallel with these 3 capacitors once I blend them together. So because they're in parallel, I can say the following. Because they're, C1, 2, 3. Because they're in parallel, par V, this is a job for par V, the mnemonic. Any 2 elements that are in parallel share the same voltage. So if my voltage drop across C4 is 12 volts, then my voltage drop across all of these 3 capacitors collectively must also be 12 volts. So at this point, I can actually say, I know what this value is right here. This is 12 volts. And you might look at and say, well, okay, yeah, this looks, this level right here looks to be the same as this level right here, but you don't know that. You can't say that. You actually have to have that whole conversation. So the voltage drop across C4 equals the voltage drop across C1, 2, 3. And that's why I can say this is 5 volts, because I am going from 12 volts to 10 volts. So that's a voltage drop of 2 volts. Then I'm going from 10 volts here down here to 5 volts. So that's a voltage drop of 5 volts. And then I'm going from here to here, from 5 volts down to 0. So that's the game I'm playing. That's my thought process for saying, okay, the voltage drop across C1 is 2 volts as indicated. Across C2, it's 5 volts as indicated. And they don't indicate what it is for V3 or for C3, capacitor 3. So that's where some thinking has to come into place. So number 1. Number 2, what's the capacitance of C1? So now C1 equals my $, and C2 also equals my $. So C1 equals the $. And then maybe I guess the first thing I'm thinking of is Q equals CV. So I'm thinking, well, Q equals CV. Does that help? Let's see what I know. What do I know? What don't I know? Similarly, the graph shows the upper part. All right. Capacitor 3 has a capacitance of 0.8 microfarad. All right. So I'm just going to write stuck. I'm officially stuck. So number 4, wait a minute. Wait, it's saying capacitor 3, the capacitance means the ability to store charge. The ability to store charge of capacitor C3, this is why we love capacitors, they store charge and have a mathematical behavior, equals 0.8 microfarad. Okay. So then, because I know the capacitance of C3 and I know the voltage drop and my voltage drop across capacitor 3 is equal to 5 volts. Great news. Great news. I can find the charge across the charge stored in capacitor C3, and that is Q equals CV. Generically, Q equals CV. Personalized for this situation, the charge stored in capacitor 3 is the capacitance of capacitor 3 times the voltage drop across capacitor 3. And that's why I can say this charge stored in capacitor 3 is going to be C3, which is 0.8 microfarads, times V, the voltage drop across 3, which through my brilliant powers of deductive reasoning, I am saying is 5 volts. And 0.8 times 5 is 4. So 4 farad volts, and a farad volt is a coulomb. Actually, here. It's 4 microfarad volts. And a farad volt is a coulomb, so it's 4 microcoulombs. That is the charge across C3. And what's so great about that? Because now it's Seri Q. Seri Q to the rescue. Because I have 3 capacitors that are in series. And make sure you're feeling comfortable in that statement. Make sure you're good to go with these 3 capacitors. 1, 2, and 3 are all in series. They're all on the same path. They're back to back to back, all on the same path. Whatever flows onto or off of capacitor 1 flows onto or off of capacitor 2 in the exact same amount is the same as whatever flows onto or off of capacitor 3 in the exact same amount. So I can say, okay, I know the charge on capacitor 3, which is going to be the same as capacitor 2 and the capacitor 1. So I'm going to just run with that. The charge on capacitor 2 equals 4 microcoulombs. And I'm going to remember the Q equals CV equation. Q equals CV personalized here. This would be the capacitance of 2 times the voltage drop across 2. I know the capacitance of 2. Oh, no, that's what I'm trying to figure. I'm trying to figure that out. So I'll do it like this. The capacitance value of capacitor 2 is going to be 4 microcoulombs over the voltage drop, which is 5 volts, which equals 0.8 micro. That micro can be left there alone. And a coulomb per volt is a farad. So I've answered part B this way using, what did I do here? Nothing. So what have I done so far? I've exploited par V. I've exploited Seri Q. I've exploited Q equals CV. So there's really not a whole lot of basic building blocks. All right. For C1, all right. C1, I'm going to do Q equals CV. So generically speaking, Q equals CV, which means C equals Q over V. Personalized, let's personalize it. So the capacitance of capacitor 1 equals the charge across 1, which is 4 microcoulombs because of Seri Q, all over the voltage drop across 1, which is 2 volts. So I end up with 2 microcoulomb per volt, or 2 coulombs. Sorry, 2 farads. A coulomb per volt is a farad. So that's the answer to part A. So that's it. We just did these 3 things: par V, Seri Q, and Q equals CV. And a very helpful visual, I think, in my humble opinion. It is now 9:17. See you at 9:26 a.m. And I'll look at Mo. I will look at your permissions and anything else. Chapter 25, quiz 3. A couple of new elements here to talk about. Energy. So we have 3 capacitors. We have 110 volt, and what they're doing here, they're saying, hey, this has a voltage drop of 10 volts. So, I mean, if you wanted to, you don't have to, because it's implied. This is what's implied. It's implied maybe that that there's a 10 volt battery here. Or you could think about it like that. So if you wanted to add your own little 10 volt battery, that would be fine. But in reality, it might not be a battery. It might just be connected. It might be connected to some other neighbor, and that neighbor is not a battery, but that neighbor does have a voltage drop itself of 10 volts. So whatever the source is of this 10, and I should say 110 volts. So you could have a 110 volt battery, or you could just have it connected to something else, something adjacent that itself has a 110 volt drop. So either way, 110 volts is applied across the capacitor arrangement. We know C1, C2, C3. What's Q3? So a whole bunch of questions. So I kind of I like these questions, like, look at it. It's like a 42-part question. It's going to take 9 hours. It won't take 9 hours, but I do like these, especially for practice, because they're going to just step us through all the basics. So number 1, what's Q3? Number 1, Q3. They're calling it little. I'll just follow their notation. Q3 is the $sign. Well, to find Q3, I'm thinking this is going to be a job somehow. Maybe this is going to be the Q equals CV equation, and then maybe other things, but Q equals CV. So I guess I have to figure out. I'm going to play the same game. Do I know the voltage drop across C3? So I do know the voltage drop. I do know voltage drop across C3. Do you know why? Because par V to the rescue. So let's do the sanity check on that. Par V says, is C3 in parallel with this voltage? And the answer is yes, they are. You might say, well, this doesn't look like the other parallel configurations, but it passes the litmus test. Here's the litmus test. Does C3 and this voltage share a common junction? Yes, they do. And you might interject, well, so does C1 and C2. That's true. But right now, we're just talking about C3 and my voltage source, whatever it is, a battery or some other neighbor. These are in parallel. They share a common nodes. So if I go this side of C3 right here, this side of my voltage, yep, they're connected to that shared node. The other side of C3 is connected to this node, and the other side of my voltage. For sure, those are in parallel. So I can say my voltage drop across C3. Voltage drop across C3 is equal to 110 volts because of par V. So then this is where I can do Q equals CV. Q equals CV personalized here means the charge across 3, I'm using capital Q, I guess, equals the value of C3 times the voltage across 3. C3 is given as 5.92 microfarads times 110 volts, 110 volts. So my calculator says 5.92 times 110 is 651.2. 651.2 microfarad volts, which is the same as 651.2 microcoulombs, because I do know that a farad volt is the same as a coulomb. That's the answer to part A. Part B says, what's the voltage? We already answered that. They're phrasing it like this. They're saying, what is the potential difference V3? So remember, one of the challenges here is these three terms mean the same thing. Voltage means the same as potential difference. And that means the same thing as just potential. So these three terms could be used, and I use them kind of interchangeably, but I usually use voltage, or potential difference is like my number 2. All right, so let's go ahead. And what is the voltage? Parv means the voltage drop across capacitor 3 is the same as V equals 110 volts. Done with part B. Part C, the stored energy. In your green sheets, some quality time in your green sheets and in the YouTube lecture video, quality was spent on the electrostatic potential energy stored in a capacitor is equal to 1/2 CV squared. So that this is saying this is the stored. So when you think of solar power or wind power, any type of new energy, we like capacitors because they store energy, and this is stored electrostatic potential energy. This is what capacitors store. They store electricity. They store electricity, and specifically the energy that a capacitor stores lives in the electric field. Because if you look at a little sidebar conversation here, if you look at this capacitor right here, and if I just say, hey, simulation, I want to see the electric field right here, electric field lines. Look at that. So that's that is. Can I change the? I can't change the area, but let me do this. So this will show it better. This is where the energy lives, and I'm kind of making a big deal about this because this is sort of gets at the essence of why one of the big reasons we like capacitors. Look at all of that stored energy. Look at those black electric field lines. All of the energy in a capacitor lives in that black electric field. If I have a little bit of voltage, look at that's not a lot of electric field right there. But if I crank up the voltage, that's look how dense. Look at that energy density. If I reduce the separation gaps, it's getting even crazier. So the energy of a capacitor lives in its electric field. So that's why I'm referring to this term as U subscript E. Generally speaking, U stands for potential energy. So whenever you see U, that means potential energy. The subscript E is saying of the electric field potential energy. I think technically it's called electrostatic potential energy, but I basically just look at this whole equation and say, okay, this is where the energy lives, or this addresses the energy living in a capacitor. So I think, do we know everything here for number 6 here? I have the stored energy in this capacitor is equal to 1/2, and we are talking about capacitor 3. So it's 1/2 C3 times V3 squared. So with numbers, 1/2 times C3, which is 5.92 microfarad. And you know what? Here, I'm actually going to do E minus 6. microfarads times the voltage drop 110 volts squared. So let's see what the calculator says. 0.5 times 5.92 e to the minus 6 times 110 squared. Okay. Joules, huh? I'm getting joules out of this. So I get 0.035816 joule. So dimensional analysis. I mean, I'm hoping I'm getting joules, but maybe I made a mistake. So I have to ask myself, what is a farad times volt squared? Well, that equals a farad times a volt times a volt. And that equals, well, I remember from Q equals CV, Q equals CV. So from a unit point of view, I do know coulombs equals farads times volts. So then this becomes a coulomb times volts. And just to continue the incredibly interesting dimensional analysis, I do know that voltage is defined as potential energy per charge, which means from a unit point of view, volts is a joule per coulomb, which means a coulomb times a volt is a joule. So, aha, I do get joules. Great success with the dimensional analysis. Got the number right. Let's move on to part D. We're going to have the same conversation for Q1. All right, so now that we have all of that, I'll keep writing here. Okay. Number 6, number 7. So rinse and repeat for Q1. Ooh, this is a little bit more. I need to find Q1. That's the dollar sign. I'm going to have to do the collapsing thing. So I'm going to do this. Here's my voltage. Here's my collapsed C1 and C2. So I'm going to combine. I'm going to collapse C1 and C2. So it's the collapsing capacitor game. I'm going to collapse C1 and C2 into just, I'll call it C1, 2. Okay. So what is C1, 2? Well, let's see. C1 and C2 are in series. They are for sure in series. So because they're in series, I'm going to say C1, 2 equals 1 over C1 plus 1 over C2. And let's get a number on that. I do know C1, 14.2, 1 divided by 14.2 plus 1 divided by C2 is 4.62 in reciprocal, all of that. I'm going to have to put this in calculator memory location A. All right, so I'm going to double check, store alpha A. C1 and C2 are for sure in series. So I'm going to combine them as series capacitors using the expression there in step 9. 1 divided by 14.2 plus 1 divided by 4.62 and reciprocal, all of them minus alpha A. Okay, so this is the game. We're back to playing the collapsing capacitor game. Step 9, step 10. I know the capacitance. I know the voltage. Well, that's good to know too. I'm going to label that here. The voltage across C12 equals V equals 110 volts. Why? Because of par V. Par V. I'm just going to make a note. Capacitor, the blended capacitor C12 is in parallel with voltage source. Voltage source, the source of my voltage. Okay, so that's an easy 110 volt. So I'm just going to annotate things a wee bit here. This is 110 volts, and the combined capacitance, color coding helps, I think, is sitting there in my calculator, memory location A, microfarads. And then I'm going to find Q. All right, so number 11. I know my voltage drop across 1, 2, and my capacitance of 1, 2. So use Q equals CV. The Q equals CV equation, personalized for this situation, the charge across capacitor 1, 2 is equal to the capacitance of C1, 2, which is calculator memory location A, times the voltage drop, 110 volts. So I'm getting alpha A times 110. I am getting 383.445 and some change micro coulombs. 383.44. All right. Good. That is the answer to part D. Brought to you by the collapsing capacitor game. Let me label this. This is the answer to part D. Just like this was the answer to part A, no, B. This is the answer to part A. A, B, C. This was the answer to part C. Okay. A, B, C, D. E says, what's the voltage drop? What's the voltage drop across stored energy for the stored energy U3 for capacitor 3, A, B, C, D, Q1, which all right, so I just did Q1, V1, the voltage drop across that. All right, so I guess that's where we are here. Number 12. Number 13, I should say. All right, what is the voltage drop across capacitor 1? So V, the voltage drop across capacitor 1 is this dollar sign now for part E. And I'm thinking Q equals CV. So I'm going to start with the Q equals CV equation and rearrange for voltage. If Q equals CV, then V equals Q over C. And specifically in this case, I have the voltage drop across capacitor 1 is the charge across. Oh, I should have introduced, hang on. I should have introduced a couple more comment steps. Because in step 12, I basically coughed up the charge across C12. I better add this. Since C1 and C2 are in series, Seri Q applies. Seri Q means the charge across Q12 is the same as the charge across 1, is the same as the charge across 2. equals 383.445. That's really the complete answer right here. So this is the real part D right there. All right. So what part E says 14. What's the voltage drop? 14. The voltage drop across capacitor 1 is what we're looking for. And this is where I said, once again, start with Q equals CV, rearrange for V equals Q over C, personalize for what we're dealing with here. The voltage drop across capacitor 1 is the charge stored in capacitor 1, which is, I guess I'm just going to have this calculator memory location B. This is calculator memory location B. So I don't have to write all that down again. Store alpha B divided by C1, and the capacitance of C1 is given as 14.2 microfarad. So let me just write out a few numbers here. So this is what was in calculator memory location B, 383.445 microcoulombs all over 14.2 microfarads. And you can see, you can just cancel the micro right on out of existence. And you have a coulomb per farad, which is a volt. All right, so what is 383 and some change divided by 14.2? It's 27 and some change. So done with this. The voltage drop across C1 is 27, almost for me, almost exactly 26, 27 and some change volts. That's the answer to part E. Part F, just go quickly. How much of that good, sweet electrostatic potential energy is stored in capacitor 1? That's what we need to find out. Let's just apply this equation, which was derived, equals 1/2 CV squared. Let's see, do you know the capacitance of C1? Yes, you do. Do you know the voltage drop across C1? Yes, you do. It's sitting right here in this calculator. So let's get the answer, just because this is plug and play at this point. That's my voltage drop squared times the capacitance of C1, 14.2 times 0.5. Okay, so interesting with numbers. Let me drag along some numbers here. If I did this, I would basically get 1/2 times C1, and this is where I'm going to have to go using my exponents. 14.2 E minus 6 farads times my voltage drop, which was almost 27. Use your calculator memory, squared. And so for me, I get this much electrostatic potential energy. 0.5 times 14.2 E minus 6 times 27 squared. Okay. This is the energy that's living in capacitor 1, 0.0511759 joules. We did the dimensional analysis before. So this is part F. Done with part F. So this is just nitty gritty, kind of repetitive, but it's good. Repetition is good, especially at the beginning. Done with part F. Onward to part G. G is saying one more time, one more game. let's use everything we've used for capacitor 2. So we're going to answer the same set of questions for capacitor 2. Okay. Getting harder to read. Number 19. Number 19. Our first stop is EFG. What's Q2? So this is going to be a similar track, a similar approach that we did for Q1. So maybe we can repurpose it. I'm going to just say C12, I know 9, 10. I know Q12. I know Q12 equals whatever I have there in my calculator memory location A from step number 12. So check out everything we did 1 through 12. Alpha A, is that still there? That's all right. I basically did the heavy lifting already to say, hey, I know the charge living, I know the amount of charge living in capacitance or C12. So whatever the charge across 1 is going to be the same as the charge across 2. And these are all going to be the same. These are going to be the same as the combined Q. The total charge in capacitor 1 and 2 collectively is the same as across Q1. It's the same across. So I've already answered it. That's why I'm done with G. So same result as the charge across charge 1 because series Q. Capacitor 1 and capacitor 2 are in series. Done with GH. H is saying, what's the voltage? This is a job for Q equals CV, which means V equals Q over C. For capacitor 2, the voltage drop across capacitor 2 is going to equal the charge across capacitor 2, which is still sitting there in my calculator memory. It's the same. It's that same number, 383.4 microcoulombs over the value of capacitor 2, which is 4.62. And I'm going to leave this as microfarads because my answer for A was already in microfarads. So for me, 23, my voltage drop across 2 is that 383.44, et cetera, et cetera, et cetera, micro coulombs all over 4.62 micro farads. The micros can cancel out and you can just do that division. $82 volts, 83 volt, 82.9. Number 24. Last but not least, how much energy lives in capacitor 2? And the incredibly elegant derivation showed that it was 1/2 CV squared. And more specifically, 1/2 times the capacitance of C2, which is given, times the voltage drop across C2, which I just figured out squared. Okay. 0.5 times C2, 4.62. And this is where I have to go from symbol to exponent. 4.62 E minus 6 times that voltage drop squared. Okay. Oh, 0.1591 joules. That's the answer to G. that was G. This was H. And this was G. F. Oh, I screwed up on my number. This is I. This is H. This is G. All right, GHI. All right, that's that. That's quiz 3. So the real new introduction here, I think, is electrostatic potential energy. This was the main, this is the big takeaway. U sub E, stored electrostatic potential energy. Other than that, it's par V, seri Q, Q equals CV, all over and over again, very repetitively. So that this is the new introduction. Electrostatic potential energy. I'll get chapter 25 quiz 4 ready. Okay. Onward, chapter 25, quiz 4. Look how little time this is going to take. Okay. Quick inventory. We have dealt with par V, seri Q. We've dealt with Q equals CV. We've dealt with electrostatic potential energy as 1/2 CV squared. We dealt with the equivalent capacitance for capacitors in series. And we dealt with the equivalent capacitance for capacitors in parallel. I think that's what we've done up till now. And then what we've dealt with what is series. So I'll just say what is series, what is parallel. And then I think, well, this is last. I mentioned it earlier, but this is the capacitor equation. Q equals kappa epsilon naught A over D. And this is it. I believe I don't think I'm forgetting anything. Well, it will be apparent when you watch the lecture video and complete the green sheets. But this is chapter 25. This is chapter 25. Maybe I need to add something but I think that's chapter 25. We have a parallel plate capacitor. So let's draw a parallel plate capacitor. Here is one plate of a capacitor, and it's a parallel plate. And again, you've actually touched upon this in chapter 22, 23, and now 25. And you'll see that again in chapter 27. So they're everywhere, these capacitors, these parallel plates. A certain parallel plate capacitor is filled with a dielectric. So here's a dielectric. So I'm basically going to I think of a dielectric as like a piece of wax. It's not, it can be anything. It could be water. Water's a pretty good dielectric, actually. All right, but I'm going to take just a block of wax. just for the sake of conversation, and say, I'm going to put a block of wax between these plates, right? Like that. So that's my dielectric. And the YouTube video, in my YouTube video for this chapter, I actually incorporate a really, really, really good set of videos from Khan Academy. And it's not Khan, it's Khan Academy for pre-med students. So if you're a pre-med student, Khan Academy is very popular to get prepared for the MCAT exam, which is the big admissions exam if you want to go to medical school. And the MCAT prep exams for capacitor dielectrics, which again, why does a medical student need to worry about capacitors, much less capacitor dielectrics? And the answer is human cells. Capacitance is a big deal. Anyway, there's my parallel plate capacitor. There's my dielectric. Kappa is basically a rating system. So what is the rating of this dielectric? And this is Greek letter kappa. It's not K, it's Greek letter kappa. So specifically, it would be a little, let's be artistic there. It's Greek letter kappa, and it's basically just dielectric constant. So it's a ranking for air. Kappa for air equals 1. Kappa for water, I think if I'm remembering correctly, equals about 160. So water, and why is that? Because water is dipolar. This is why we studied polarity and dipoles, and we studied dipoles in chapters 22 and 24. And now we're seeing the effects of dipole here in the case of dielectrics for capacitors. So the Khan Academy, I don't want to steal the thunder. I don't want to replay all of that because you should have already watched it, or you will. But it's basically saying a dielectric alters the electrical properties of a capacitor. Dielectric alters the capacitor's electrical properties. And what kind of electrical well, it alters the capacitor's electrical properties in desirable ways. And there's sort of one of two ways. If I insert a dielectric, like you see here, I can have greater charge stored at a given voltage. Or if I prefer, with this dielectric, I can have a much greater voltage for the same amount of charge. So you'll get a very good overview of that at a very nice low level, fundamental level. That's not massively deep, but it's going to show you why we like dielectrics. We love capacitors, and by association, we love dielectrics because dielectrics alter the capacitor's electrical properties in ways that we like. So there's my basically block of wax with a dielectric constant of 4.54. I know the plate area, so I'm looking at this edge on, but here's what these plates look like. These plates look like this. So you can see me altering the plate area. What if I want a small capacitor plate area? Look how small that capacitor plate area is right there. Look how big it is here. And conversely, I can alter the gap, the plate gap. Here is a small separation. There's a big old separation. And as long as I'm here, this is what I'm doing. There's my dielectric. So I can change my plate area. I can go crazy to change my plate area. I can change my gap separation. I can go small or large. And then here's me putting a chunk of wax. Ready, set, go. There. There's the wax that goes between the plates of my capacitor. And then, what if I want to use glass? Here's glass. Here's paper. Here's Teflon. And here's my own custom engineered material. But Why do I deal with this dielectric? Because it alters the electrical properties. And let's just turn well, let me turn on the meters, capacitance. So watch what happens. Watch what happens if I don't need this meter. Turn on the battery. Look at that. Look at that. Now watch what happens here when I remove my capacitor. So when I remove this capacitor, everything's changing. I mean, when I remove the dielectric. So no dielectric. Notice I have a certain capacitance, plate charge, stored energy. My battery is just sitting there at 1.5 volts. So my battery remains connected. So watch what happens to capacitance and the charge and the energy. Here's what's going on with no dielectric. Ready? Here's what's going on when I add a dielectric. My capacitance is increasing, my plate charge is increasing, and my stored energy is increasing. This is why we like dielectrics. And I'm doing this all the while the battery's connected. What if I went back to square one and I disconnect the battery? So there. Now what happens when I put my dielectric in there? Things are changing, but not the charge. So this is pretty cool because even without my capacitor connected to this battery, I can still, look what I'm doing. I can actually alter its electrical properties. In this case, the capacitance is increasing. The plate charge remains unchanged and my energy actually diminishes. And you might want to do this in certain instances. So these are the two reasons why we like dielectrics. Disconnected from the battery, I can actually increase the capacitance for a given voltage. All right, so much more on that later. Well, not much more. That's kind of it. All right, so I know all of my stuff. I think I know everything for my capacitor equation because my capacitor equation is saying step one. My capacitor is saying, hey, the capacitance is equal to the dielectric constant times the permeability of free space times that plate area all over distance. So this is foundational, which is why you see it here. It's in the Hall of Fame. So this seems so easy now. Let's see. What is the maximum energy? What is the maximum energy? So I guess I really should start with, this should be my step one. I want to know the maximum energy that I can cram into this capacitor. So let's start with what is the maximum potential energy? That's my dollar sign. Maybe I'll do like this, max. Electrostatic potential energy is the dollar sign. And the answer is very quickly, the potential energy, which is stored in the electric field, is 1/2 CV squared. Okay, I don't know any of this. So I don't know C and I don't know V, but I do know some physical properties and some geometry and the electric field. All right, so number 3. What's C? What is C? And the answer is C equals kappa epsilon naught A over D. So with numbers, the capacitance of this capacitor is kappa 4.54, that's the dielectric constant, times epsilon naught 8.85 E minus 12. And I'm going to drag along the units. Let me get the units on this because I actually don't remember off the top of my head. This is the permeability of free space. Oh, actually, I can look it up here. Yeah, permeability of free space. Let me just give me a minute to get the right units on this. 8.85 e to the minus 12. And let's see, units could be, I need to get the right units. Well, I'm going to have to go to my lecture notes. 1 minute. Calling up the chapter 25 lecture notes. Okay. I know this. Oh, there it is. I found it. Okay. So in the lecture notes, let me take a snip. Okay. We can't pretend not to do. We can't pretend to ignore, or we can't ignore dimensional analysis. All right. Here's the permeability of free space with an alternative set of units. It's right there. Okay. 8.85 E minus 12 farads per meter times A, the cross-sectional area for this capacitor in my case is 0.0315 square meters. That's again the plate area. All of that divided by the gap. And for me, my denominator is the plate separation between these plates, which is given in my case as 2.42 E minus 3 meters, converting from millimeters to meters. All right, so I'm going to get a value here and store it. 4.54 times 8.85 E minus 12 times 0.0315 divided by 0.00242. Store alpha A and do it again. Oh, 315. Okay. So I know my capacitor. I know the capacitance of this capacitor, its ability to store charge. It's just going to, well, for me, it's 5.22 E minus 10 farads. And yeah, the dimensional analysis does come out. If I have farads here, farads, square meters, and then the square meters cancels out. So dimensional analysis looks good. This, I'm going to put this in my calculator memory location A, but now I have to figure out what is the voltage of this across this capacitor. Now we're going to have to re-engineer. I don't know the voltage, but I do know the electric field. So I think I can leverage that. And this is for sure a chapter 24 entity that was covered in actually pretty good depth. Number 6, number 7. All right. What is voltage across the capacitor? What is voltage across the capacitor? And the answer is, I don't know, but I do know that the electric field. So from chapter 24, you should remember this. From chapter 24, at some point, this is going to have to look, maybe it does now, but if it doesn't now, it needs to. We actually had this expression. We actually said E sub X equals negative delta V over delta X. And then we had a whole bunch of other alternatives. We had the electric field in the Y direction equals negative delta V over delta Y. And then we had this one. And you need to remember this and you need to apply it. And then especially remember we had those partial differentials, negative dV dx, partial for the x, partial for the y. There's, I think, 2 homework problems that relied on this. So I'm just recapping this here just for the sake of remembrance. Ez equals, so anyway, partial derivative of voltage with respect to z, and we can leverage this. So I'm actually going to use this expression right here. It's that easy. And I wrote down all this other stuff just for reinforcement purposes, just because nothing is expendable. There's no triage you can do on these green sheets. Everything's in. Everything has to be, every patient must be saved. So I'm going to say, aha, since here's the relationship between the electric field and voltage. I guess I better do, I'm going to just call this plus x. So there's my coordinate system. Aha, since that's true, and that was its own derivation, then I can say this. I can say delta V equals negative EX delta X. This is great news because this is how I'm going to be able to get the voltage. So this is me saying, if I know the electric field lines, if I know all of these electric field lines going across this plate, there's a whole bunch of electric field lines. If I know what that electric field strength is, and I know the distance across which this electric field acts, I can use that to find the voltage. So number 10 says that voltage, this change in voltage across those plates equals negative 154,000 newtons per coulomb. And I'm just picking up on this number here. 154 kilonewtons. Kilo is 1,000. So my electric field's pretty darn strong between those plates. It's 154,000 newtons per coulomb. And then what's the distance through which that voltage or that electric field is acting? For me, it is 0.00242 meters. And that is because of this specification right here. Now, I don't care about the negative. I'm going to ignore the negative. So I'm basically just going to X out the negative. I don't care about if my voltage is increasing or decreasing. If I did, then I would have to worry about that negative. So I'm not going to worry about, hey, what's the direction of the electric field? Is my voltage increasing or decreasing? So I'm just going to ignore that. And I'm going to put this result in memory location B. This is my voltage. 154,000 times 0.00242. Store enter calculator B. And then number 11. Once again, the energy living in this capacitor is 1/2 CV squared, which for me is 1/2 C, and C is sitting there in memory location A, and my voltage is sitting there in memory location B squared. So what is 0.5 times alpha A times alpha B squared equals 3.6319 e to the -5th joules. You should do the dimensional analysis, but that's a good problem. And I really don't think there's anything new going forward. So let me give a nice cordial see you at 10:30. Okay. Chapter 25, quiz 5. Two more to do, which could mean the unthinkable. We could finish early. There's nothing new here. So this is just a different application, but the good news is all the new stuff I think is behind us. We have two capacitors in parallel, C1 and C2. We know all of the material and geometric properties. How much charge is stored in the figure? How much charge is stored on the parallel plate capacitors by the battery? So this is what we're after. We're after how much Q12 is the dollar sign. How much charge is stored on the parallel plate capacitors by the 12-volt battery? One is filled with air, the other is filled with a dielectric for which kappa is 3.8. Both are, and so we know about all this stuff. So number Q12 is the dollar sign. So my first thought is Q equals CV. How much charge is stored in these capacitors? And the answer is Q equals CV. That's how much charge is stored. So what's V? And the answer is V equals 12 volts. That's pretty easy. And this is par V. This is a job for par V. Par V means any two devices that are in parallel. Let's see. Here's my voltage. See, that's for sure parallel. So my voltage supply, my battery, and C1 for sure in parallel, par V. And then if I have the same conversation, here's my voltage and here's C2. Yep, they are in parallel because they share that same node with nothing between them and their shared nodes. Okay, so I'm feeling okay about that. So let's figure out number 3. Let's combine. Let's combine C1 and C2. Because C1 and C2 are in parallel, I can use the equivalent capacitance for parallel capacitors, which basically says the following. C12, that equivalent capacitance, C12 is just going to equal C1 plus C2. Don't be confused. If these were in series, I would say C12 equals 1 over C1 plus 1 over C2, but it's not series. These are not in series. They're in parallel. So C1 plus C2. Do I know? I don't know any of these values. So let's find out. What's C1? What is C1? Number 6. It is C1 equals kappa permeability of free space area over D equals kappa. So here's one. There's my Oreo with a creamy white filling, and that creamy white filling has a dielectric constant of 3.80. 3.80 times 8.85 E minus 12. And the units there were, I got to remind myself what those units were. The units were farads per meter. 8.85 E minus 12 farads per meter times the plate area, which is 9.5 E minus 3 meters. That's given. All of that over the gap distance, which is 7.5 millimeters or 0.0075 meters. So I'm going to just put that in calculator memory location A. 3.8 times 8.85 E minus 12 times 9.5 E minus 3. Okay, let me redo. All right. What's C2? Well, here's C2. C2 also equals kappa epsilon naught A over D. Everything's the same except there's no dielectric constant. So it's just going to, well, I'm sorry, the dielectric constant is 1 because the dielectric constant for air is about the same as it is for a vacuum. It's pretty darn close to 1. So what is 1 times 8.85 E minus 12 farads per meter times 9.5 E minus 3 all over 0.0075 meters. And I'm going to put this result in calculator memory location B. Okay. So onward. What is C12 again? C12 equals C1 plus C2 because they're in parallel. The equivalent capacitance for capacitors in parallel is given right there in statement number 4. So then we can just find out what is calculator memory location A plus calculator memory location B. And I'm going to, whatever that is, I'm going to put in calculator memory location C. Alpha A plus alpha B store alpha C. All right. Number 9. Aha. I know the following. I know the voltage drop across C12 is 10 volts, 12 volts. Mine says 12 volts. It's 12 volts because that's the battery voltage, and C12 and that voltage are in parallel. And I now know that C12 itself, the capacitance of C12 is sitting there in memory location C. So this is a job for Q equals CV. Q equals CV, which is calculator memory location C times 12 volts times 12. Okay. 6.456 and some change E minus 10 coulombs. That's it. Because I had a farad times a volt. Okay. All right. Nothing new, just a different example, just a different application. Nothing new. Last quiz. Let me just check something. Yeah, so you know what? We're going to do every homework problem except for the 2 deep dives. And I can tell you guys, I don't know if all of you are really learning all you can learn from the deep dives or actually from these Zoom sessions. I mean, I think a lot of you guys are going to be very well served to rewatch these lecture videos. This looks pretty. Let me get it ready. So, I know what I'm going to do for this last one. All right. I'm just going to say a few comments here. Let's see. This is chapter 25, quiz 6. It's 10:40. I'm going to go crazy and just put this open to lunchtime, 11:59 a.m. Okay. Which is literally almost 90 minutes from now. There it is, chapter 25, quiz 6. Okay. So I'm just going to do some hand waving here. I'm going to do this. I'm going to just index everything. Nothing new here. Absolutely nothing new. Just some practice for collapsing capacitors. Really, when you go through this, it just reinforces the heck out of when you do this type of problem. It's definitely stressing par V, seri Q, Q equals CV, CEQ for parallel, CEQ for series, and just what is meant by series and parallel. So anyway, all right, so I'm going to index a C1, C2, C3, C4, C5, C6, and C7. Okay. C1. All right, so let me just C1, C2, 3, 4, 5, 6, 7. All right, so our first stop, number 1, what is the charge on capacitor 1? That's the $sign. All right, so I'm going to do it like this. I'm going to collapse. Let's see. Number 2. C3 and C4 are in series. So that's, I can see that. So here's my first diagram. I'm going to just do, what's a good way to draw this? I'm going to do C1. There's C1. And then when I put C3 and C4 together, they're going to look like C34. Okay, and those are in parallel, and they're in parallel with my battery. C1, am I drawing this right? Because basically I can collapse all of this. These three blue dots kind of collapse into one. Okay, so I've collapsed all of those blue dots into one dot, and same for these two. So I'm just being careful. I want to make sure I'm collapsing things the right way. So C3, C4, the top connects to C1. That's right. The bottom connects to the battery. Okay, I think this is good. All right. And then if I look at the lower branch there, I see C6 and C2. So here's C5. There's C5. And then I'm going to combine these guys into C26. And then this will be C7. I'm going to have to draw it like this. Let me erase. So this is the trickiest part, just figuring out this stuff. Okay. Parallel. What's a good way to draw that? C26. I guess I'll just do C26 and then C7. I'll draw it like that. That's fine. Okay, so I have this, which is, believe it or not, a simplification. And I'm just going to be really careful here. I don't want to go down any wrong turns. C5 looks good where it is. C2, 26. This looks good. I'm connected to the right side of the battery. That looks good. And C7 is in parallel. This is good, I believe. And then I'm going to combine C26 and C7. So I'm going to do, here's C34 unchanged. Here's C1. They're in parallel. Here's my battery. Here's C5, no change there. The only change I'm making, because I'm going in teeny tiny steps, is this is going to be C267. Okay. Okay. And I guess that's it. I can go from here to here to here. This is going to be C341 battery and C5267. Okay. This is voltage C341. And then, I don't know, you guys, to me, this is going to take just too much time. I think this is going to take too much time, even though it's only 10:47. I want to hold off on this. Let's not do quiz 2556. I want to revisit this just because maybe we'll do it in class. I don't think we're going to have enough time. Well, tempted not to do it, but I'm tempted to do it because it's not that, well, it's pretty messy actually. Capacitor charge on capacitor 1. Well, let's stick with this. So hemming and hawing aside, because we don't have to collapse any further than this point, because right now the charge on capacitor 1, it lives in here. So here is the charge on capacitor 1 lives here, and the charge in capacitor 2 lives here. This is Q2, and both of these are the dollar signs. So let's spend a bit more time. If it's looking like this is going to go just be too laborious for the time we have remaining, I can cancel this and return to it. But let's see right now. Let's just go ahead and hammer on this for right now. Let's see how long it's going to take us to get Q1, the charge across capacitor 1, which is right here. All right, and I'm going to just double check. This was my starting point, and then I went from there to here. This is C34, definitely in parallel with C1. Okay. C34, C1 battery. Okay, so let's find number one. C34 equals 1 over C3 plus 1 over C4 equals 1 divided by C3. They're all 16 microfarads. 1 divided by 16 plus 1 divided by 16, reciprocal that, 8. So C34 is 8 microfarads. Okay. I actually think I have to modify this drawing, because as I'm looking at this right here, I think to actually reconfigure it correctly, if I put, there's my battery voltage, here's C34, and in parallel with C1, this is C34, this is C1. Yeah, I think I have that basically. So I need to do a little tweak on the drawing here. I can save the work I did But I believe if I'm redrawing it correctly, I have my batteries here, C34 blended into this capacitor here, and C1 is in parallel. Okay, so that's it. I'm going to make this modification. Good thing I do it now instead of later, but I basically have this. This is C34, and this is C1. That's C1. This is C34, which has a capacitance of 8 coulombs, 8 microfarads, sorry. This is C34. Okay, my battery is 16 volts, which means this is 16 volts, which means this is 16 volts because of par V. Okay, this C34 capacitance was 8 microfarads. And I don't think we actually need that at this point. C1, we need this charge. So 16 volts across C1. C1 has a value of 16 microfarads. So maybe this is a lot easier than I thought. We'll see, because number two says the value of C1 is equal to 16 microfarads. The voltage drop across C1 is 16 volts. So if I use the Q equals CV equation, Q equals CV, I have 16 microfarads times 16 volts equals 256 microfarad volts equals 256 microcoulombs. So, okay, that turned out to be not as heavy as I thought. So we're done with part A. Part B, what's the charge on capacitor 2? Okay, and this is where I'm not trusting myself, so I'm just going to double check again. I want to check my collapsing diagrams. So I don't care about this upper. I am done. I am completely done with the upstairs portion of the circuit. I'm just going to really focus on the downstairs portion, which is what I'm highlighting here in yellow, because there's where my dollar sign lives for part B. All right, so I'm just going to do a quick little discount check. C5 is good where it is. My battery is good where it is. C26 is good where it is. Is it? Because those are going to be, I think this is good. I think that's good. C26 is definitely in parallel with C7. So I'll go with that. All right. So now I'm going down here, I'm looking here. There's my battery. There's C5. There's C267. That's good. Now I'm going to go here. There's my battery. Hang on a second. There's my battery. There's C5267. Okay. All right. So I think this is good to go. Step number 3. Well, here. I know this voltage. This voltage here, this is 16 volts par V. Par V says these two devices, these two elements are in parallel. 16 volts here means 16 volts here. So let's get the total charge in this assembly. Step number 3. What is the total charge in 5267? 5267. Q equals CV. I guess I better get 5267 equals, I'll just do it like this, C of 5267. Let me back up. Okay. That was a little bit too early. Let's get C26. C26 right here. Those are in series. So C26 equals 1 over C2 plus 1 over C6. I'm going to put that in memory location A. So C26, everything is a 16 microfarad capacitor. Is it? Just double checking. Yes. So this is going to be 8. This is going to equal 8 microfarads. Got it. That's C26. What about C267? C267, those are in parallel. So number 4, C267, because they're in parallel, it's just C26 plus C7 equals 8 microfarads plus C7. Everything is a 16 microfarad capacitor equals 24 microfarads. So I have C267. Number 5, I have C5267. Let's see, here's C5. These are in series. C5 and C267, they are in series. So that's going to be 1 over C5 plus 1 over C267, or 1 over 16 microfarads. I'm just going to use U. U means microfarads, plus 1 over 24 microfarads. So what is 1 divided by 16 plus 1 divided by 24? Reciprocal of that, 9.6. 9.6 microfarads. I'm just going to do a double check. C5, C267. I think this is a good. Okay. That's it. So I know this charge. I'm sorry, I know this capacitance value. This capacitance value is 9.6 microfarads. The voltage across it is 16 volts. So number 6, the charge across 5267 is Q equals CV. Here's C, 9.6 microfarads. Here's V, 16 volts. That equals 9.6 times 16 is 153.6. 153.6 microcoulombs. Okay. Because they're in series, everything in series, series Q. So it's off to series Q. Series Q means if 5267 has this much charge and they're in series, that means this has 153.6 microcoulombs. And because they're in series, this has 153.6 microcoulombs. And there's C2. C2 is living in there. Let's find the voltage drop across that. Number 6, number 7. What is the voltage across 267? This is a job for Q equals CV. If Q equals CV, then V equals Q, 267, all over C, 267. With my numbers, Q equals CV, I have my charge is 153.6 microcoulombs all over the capacitance of 267, which is sitting there right here, 24 microfarads equals 6.4 volts. Nice numbers. I mean, not nasty numbers. That's it. I have the voltage across C267. So you know what that means? We're going now up here. This voltage here is, for me, 6.4. 6.4 volts for that capacitor, 6.4 volts for that capacitor. Why? Because they're in parallel, par V. And then I think just we're definitely on the final stretch here. I know this is intense, but it's going pretty quickly. It's going pretty quickly, unless I made a mistake here. In that case, we'll figure out something. Okay. Number eight. All right. I know the voltage across C26 is 6.4 volts. I know the capacitance of C26 is equal to C26 is 8 microfarads. So you know what that means. I can say Q equals CV. The charge stored in C26 is equal to Q equals CV. 8 microfarads is the capacitance times the voltage, 6.4 volts, equals times 8. 51.2, and we're done. 51.2 microfarad volts, which is the same as 51.2 microcoulombs. That's the charge across C26. So right here, if you look right here, Seri Q, C2 and C6 are in series. So Seri Q applies. And because Seri Q applies, it means whatever the charge is across C6 is the same as the charge across capacitor 2 is the same as the charge across C26, which is what I just figured out here. So the charge across capacitor 2 equals 51.2 microcoulombs. That's a lot. That's a lot, I guess. And we're done. What time is it? 11:03. We're still done early, a half hour early. But you guys might need some more time. So, but that's it. There's nothing new. So we've covered, there's not going to be any hidden surprises. There are no additional introductions. This, I'll put that screen back. I'll put the screen back, but this is, I believe, everything that's in scope for chapter 25, and then just practice. All right. So before I'll leave the screen.
So is it too late to like open up old quizzes? Or?
Yeah, you have to open up. I'm happy to extend deadlines, but it has to be on the day of. You can't say, hey, can you open a quiz from like 3 months ago? Because we have to kind of stay paced. So feel free to request an extension, but it has to be day of.
All right.
Okay. So we'll see you guys on Wednesday or Thursday, I should say.